In this video, we are going to be looking at the use of methods based on backward induction as the basis for practical algorithms for playing games. We're going to focus on zero-sum games. So previously, we've only looked at zero-sum normal form games, but the definition of zero-sum also works perfectly well for extensive form games. And many standard games that we're interested in developing AI algorithms for are zero sum. These are things like chess and Go and that kind of thing, board games. These are kind of standard challenges in AI since many decades. In this case, so in the case of a two-player zero-sum game, we can basically simplify and say we only have one payoff, and we think of player one as the maximizing player and player two as the minimizing player. That's a kind of equivalent formulation of zero-sum games. That's equivalent to player two minimizing is equivalent to player one maximizing the negative payoff. So yes, lots of real-life games have this form, and kind of obvious barrier is that for basically all of these, if you actually think about what the tree of all possible moves will look like, it's going to be too big to do anything with. The number of nodes in the tree is much larger than the number of atoms in the universe. So we want to kind of explore this tree, but we can't do backward induction because there's just too many nodes. So instead, we're going to explore the tree in a heuristic way to try to estimate what are good moves. As a small change of perspective, we're going to view backward induction. Instead of deleting nodes, we're going to be annotating nodes with the payoff. So we're going to say the payoff for player one. So that's just a small change of perspective that we're going to be talking about algorithms that kind of traverse through a tree and annotate nodes with the payoff of optimal play from that node. So first thing we need to do is we need to limit the search depth in the tree, because that's the main thing that's causing the kind of explosion in the number of nodes. So what is done in practice is, remember, when we have a particular specific game, we know more about it than just the mere fact that its plays form a tree. So if you think about the game tree of chess, for example, every node is not just a mere node, it represents some particular state of the game board. So for example, the root node of chess means the initial configuration of a chessboard. And what we can do is we can have heuristics to estimate the value of a position without doing any look ahead. So for chess, you can do things like just add up the values of the surviving pieces, or kind of there are more advanced heuristics that are kind of specialized to details of chess strategy. So the first thing we can do is we can limit how far ahead we look by saying that once we have gone some number of nodes ahead of where we started, we kind of give up on backward induction and we just fall back on the heuristics to solve it, or to approximately solve it. So this is the core idea of a lot of classic game playing methods like chess engines. Another thing, of course, we can do is that the look ahead depth doesn't have to be fixed. We can dynamically adjust that based on heuristics as well. So chess engines will dynamically adjust how far they look ahead depending on how kind of intricate they believe the position is. So they look further in kind of very complex paths where there's kind of lots of trading of pieces and that kind of thing. Whereas in very static positions, they look ahead less far. Okay, now there's a method called Alphabeta pruning, which is a kind of obvious and very valuable method to speed up backward induction for, this is specialized to zero-sum, two-player zero-sum games. So we can rule out subgames very quickly. So the idea is that while we're searching, we're going to keep track of two values. One is, which is called alpha, is the best known value that player 1 can get, assuming that player 2 plays optimally. And beta is the best known value that player 2 can get, assuming that player 1 plays optimally. And so the idea is that if at any point player 1 can reach a value that's higher than beta, then we know that player 2 is never going to allow us to go that way, because the point of beta is that it represents a value that player 2 is able to force. So if we're doing better than that, then we know that beta is never going to allow, player 2 is never going to allow us to get that value. So it means that we can just stop exploring that branch. Player 2 will never allow us to go down that branch, and so we just never need to look at it. And similarly, if player 2 reaches a value that's lower than alpha, then player 1 will never allow us to go that way, so we can stop exploring. So here's an example. So suppose we're exploring this tree. So I've labeled these nodes by max and min. So the max is the maximizing player, min is the minimizing player. So suppose we first go down the left branch. So we reach here, and so we now have that the maximizing player is choosing between 4 and 3 in this branch. So we know that the maximizing player is going to choose 4. So in this case, we set alpha to 4. Now we have to explore this branch because we're trying to solve for this player, so we need to explore the 2 sub branches here. And now we know that after we look here, so we look at this node and we say that if we were here, then player 1 can get a value of 6. So we set alpha to 6. Now, instead of going here, let's think about the situation here. The minimizing player has to choose to go this way or this way. And we know that if we go this way, then player 2 is guaranteed a payoff of 4, or let's say -4, because we're thinking of player 2's payoff as the negative of the actual payoffs. And so there is no way that player 1 will go this way. There's no way that player 2 will go this way, because if they did, we know that player 1 can force a value of at least 6, no matter what's in this branch. We never have to look at this branch because we know that player 1 can get at least 6. And because that's larger than 4, we know that player 2 will never take this branch. So we can, at this point, we can stop exploring this and backtrack to here. So this branch is never explored. So that's an example of just not looking at a leaf, but this can also happen where we cut off an entire subtree. So at this point, we know that player 1 can get 6 if we go to here. Player 2 can force 4 if we go to here. Now, suppose we go this way. So at the root node, player 1 is choosing between going left and right. So now explore down this leftmost branch. So now we know that if we go here, then player 1 will get 2, or that is to say, after exploring both leaves of this node, we know that the payoff will be 2 here, because player 1 is going to choose this branch. Now, if you think about it, the fact that that the payoff here is 2 means that if player 1 chose to go this way, then player 2 can force 4, which means that if player 1 chose to go this way, then player 2 can force at most 2, no matter what's in this branch. So possibly player 2 could do even better by going this way, but we know that player 2 can force the payoff as low as at least 2. So what that means is that player 1 immediately knows that they never want to go this way because they can guarantee to do better by going this way. So what that means is that as soon as we get as far as this node, we can cut off this entire branch. We never need to explore here. And at this point, we can say for sure that the equilibrium play here is player 1 goes left, and then player 2 goes left, and then player 1 goes left. We're going to end up here. Okay, there are more advanced heuristic methods than just alpha-beta pruning. Monte Carlo tree search is a family of methods which are basically reinforcement learning methods for exploring a tree. And so even though the game itself is deterministic, we're allowed to use randomness in heuristics to try to do well on average. So the idea of Monte Carlo tree search is that we're essentially going to explore the tree at random. So we're going to kind of run plays of this game at random. And every time we complete a play, we're going to update our estimates of all of the actions that we chose during that play. So initially these are random, but we can kind of try to award kind of credit for the payoff that we got to various choices that we made along the way. And so by doing this several times, we end up with estimates of a lot of actions along the tree. Now, at this point, if we're playing for real and these runs of the game are actually happening for real, then we have to be careful between the usual reinforcement learning thing where we try to exploit by doing actions that we've already figured out are good versus exploring and trying to find something better. So this is a method where we do a mixture of sometimes choosing actions which maximize our current estimate of the value of that action versus sometimes choosing actions that we haven't explored yet that don't yet have an estimate. So the details of this method are pretty complicated. So we're going to come back to this kind of thing in the last few weeks when we're going to look in much more detail about reinforcement learning. But I can say that Monte Carlo tree search is basically one component of a lot of state-of-the-art methods like the AlphaGo and this family of methods. So this is basically Monte Carlo tree search combined with a lot of other more modern methods like deep reinforcement learning. So typically we have a state space which is extremely big, and so the representation of the mapping from nodes of the tree to estimated values is actually a big object to represent. So typically we're going to use something like a deep neural network to represent that kind of family of approximate values that we found so far. And of course, it's also combined with more state-of-the-art reinforcement learning methods that for doing things like being very careful about when we choose to explore, when we choose to exploit, this kind of thing, and the order in which we update our estimates.